Separation of variables and the logistic equation. While not all differential equations can be solved explicitly, any differential equation can be solved if you can separate the variables and then use proper rules of integration. So we're going to find the general solution for this equation, x squared plus 4 times dy dx equals x times y. So we're first going to put it into differential form, which gives us x times y dx. I have my dy on this side, and we're now going to separate the variables, which means move the x terms to one side, the y terms to the other side with a little algebra. You can see we get that done here. And this is called separating the variables. All y's on one side, all x's on the other side. Now you will notice if our u is x squared plus 4, our du would be 2x dx. So I need to multiply and divide by 2 to get this to be something we can integrate nicely. So the antiderivative of dy over y equals the antiderivative of x over x squared plus 4 dx. Modifying this side gives us 1/2 the integral 2x over x squared plus 4 dx. Notice that is u prime over u form, which we know integrates to natural log of absolute value of u. And so what we get is ln of natural log of absolute value of y equals 1/2 natural log of x squared plus 4 plus some constant c1. Now let's remember, we have that constant of integration on both sides of the equation when we antidifferentiate. And so I am saying, let's just let this constant we don't know be the collapse of these two constants we don't know. So my C3 minus C2 is going to be C1. And let us remember that I want to be able to work with my natural logs. And so I'm going to convert this to a term that involves natural logs. So let's let C1 be natural log of C. And now I have the ln A plus ln B property, which allows me to write this as natural log of C times the square root of x squared plus 4. Now, if I treat each of these as exponents on e, that would be e to the natural log of absolute value of y equals e to the natural log of c times x, the square root of x squared plus 4. Remember, e to the ln u is u, so e to the natural log of absolute value of y is absolute value of y, and e to the natural log of all of this gives me c times the square root of x squared plus 4. Now that is one way to get to this general antiderivative equation. But I also could have come here. I could have written that this is my to the 1/2 here, which gives me this square root. And this becomes y, and this becomes e to this power. So we get down here either way. Just another way to think about it. And I don't need the absolute value bars anymore around y, because we know that the square root symbol means to give the non-negative part of this. And we know that this c came from e to the c1. And e to any power is going to be positive. So e to the c1 is positive, making c positive. So that is why we can remove those bars. Example 2, find the unique solution of x times y dx plus e to the negative x squared times y squared minus 1 dy equals 0 for this initial condition. First, we want to write this in differential form, which is going to have my dx on one side and my dy on the other. So I'm going to subtract this from both sides. Now we want to separate our variables. Remember that separating the variables means to move the x terms to one side, the y terms to the other side. So the y's, this could divide by y, and I'm going to divide by e to the negative x squared. Dividing by e to the negative x squared is actually times e to the x squared. So we can simplify this fraction by thinking about this as y squared over y, which becomes y, minus 1 over y dy. So we can see that's not going to be too terribly difficult to integrate. And then here I have e to the x squared times negative x dx in this problem My u would be x squared. My du would be 2x dx. That's what I need, is a 2x dx. Okay, I have the x part of it. I don't need the negative, so I'll move that out in front. And to get that 2, I'm going to multiply and divide by 2. So this right here is going to become this right here. Negative 1/2 2x dx times e to the x squared. We know that is going to integrate to e to the u. I have it in e to the u du form. Will integrate to e to the u. Here we're going to make two separate integrals. This anti-differentiates to y squared over y minus, this becomes natural log of y. Okay? And this will become negative 1/2 e to the x squared plus my unknown constant c. Now, why do I not need bars here? Okay, I do not need bars because y is going to be, when x is 0, y is going to be 1. So, substituting in my value, I get my c to be 1. And here is our wonderful equation. That looks pretty ugly. Okay, we can use algebraic properties to simplify it, multiplying everything by 2. And then bringing the variable terms to one side and constants to the other. You don't have to do it this way. However, you might have to be able to do that algebra to get your answer to match a matching answer. So now we can see why Leibniz's notation of dy dx is more useful than Newton's notation of y prime. And I will leave to you looking at pages 421 to 424, examples 1 through 5 for more examples. Now let's look at one more. This is one you'll have to write out. Example 3, find the equation of the curve that passes through the point 1, 3 and has a slope of y over x squared at any point xy. So first, dy dx is y over x squared. Next, we're going to find an equation, separate our variables, dy over y equals dx over x squared. That's a point for separating variables. Now we're going to anti-differentiate both sides. Gives us this. So I get a point for this antiderivative, a point for this one, and a point for the constant of integration. And this is a form of the general equation. Now what we know is it passes through the point 1, 3. We also know log is exponent. So this is another form of our equation. Through the point 1, 3, our y is positive. So we need our positive y, not the negative y. We know that e to the negative 1 over x plus e to the c1 is e to the negative 1 over x times e to the c1, which is y equals c e to the negative 1 over x. We know all this. Now this is your best general form. And now that we have the point 1, 3, we can substitute 1 for x, 3 for y, and we get c to be 3e. So we call this using our initial condition. And then solving for y. Okay, it says find the equation of the curve. That means solve it for y. So y is equal to, here's my c, e to the negative 1 over x. That's an okay answer. Right? But if we think about this, this is e to the 1 times e to the negative 1 over x. So that's e to the 1 plus negative 1 over x, which becomes this. That is your best answer. All right, I will pause the video and let you write down this problem. Your TPs for this section are 5, 7, and 9. See you next time.